well, I see at least 3 organizers here, which I think means we have a quorum. Thank you, everyone, for being here for the 3rd lecture in this series. We're going to talk finally today about how to show that our estimate x hat is going to recover those true x's we were talking about. So I'll start today's lecture by just refreshing some of the notation and setup from the random dot product graph. We'll see a kind of prototypical result under this model that sort of tells us how fast we can recover those true x's based on a spectral estimate. We'll talk about why spectral estimates are kind of natural for this problem. We'll talk about how to measure that error. Right? We kind of left off yesterday's lecture saying, like, we're going to measure some norm of x hat minus x, but we kind of left it a mystery what that norm's going to be. We'll fill in that question mark. And then we'll use the second half of today's lecture to actually talk about how we prove these bounds. And basically, they boil down to concentration inequalities. We have some world experts on those tools here with us today. But somehow I'm lecturing at some of those world experts, which is a very intimidating thing to be doing. But I'll point to some of those results, and we'll see an illustration of those tools. Because of time, we're not going to see kind of the most technical or the most optimal such bounds, but I'm going to show you some of the basic tools that we tend to use in those results. And since we have world experts here, they can fill in some of the gory details for you when there's not a timer running up to afternoon coffee. So with that, let's dive in. So our setup was that we have a graph drawn from an RDPG, random dot product graph, with latent positions x. So x here was an n by k. Sorry, it's always d for dimension in a lot of the papers out of Carey Preve's group. Again, we're imagining k like to match the number of blocks. So forgive me if at some point I slip up and say d dimensional instead of k. The rows of x, 1, x2, the rows of x encode something like the role of every vertex in our graph. Right? So once I tell you the latent position, the xi, for some vertex I, you know basically how that vertex is going to behave. Right? The reason being that conditional on these latent positions, edges are independent Bernoulli xi transpose xj. Okay. One note that I'm going to make here, in most of today's lecture, I'm not going to include a sparsity term here. It's just because the sparsity term becomes one more thing you have to track through all of the proofs. So I'm going to basically do most of our presentation today ignoring sparsity. Where relevant, I will point out kind of how sparsity comes into play and kind of what rates we can and can't get. Okay, but just to simplify a lot of the presentation, I'm going to imagine we're in this like beautiful world where the network is dense, and like the more people join Facebook, the more friends everyone has on Facebook, right? It's like this is, so like I mentioned yesterday, usually we're going to want to put some sparsity parameter on this x, right? Drive the x's towards 0 as n grows to keep the network comparatively sparse. I'm going to suppress that for most of today's lecture just because a lot of what we're going to be talking about is like, you basically replace n with n times rho to get the rate with sparsity. And I want to more focus on the techniques than on chasing this one parameter around. Okay? So that's our setup. And so our goal going to be to recover x. And of course, we can only do that up to some rotational non-identifiability, or excuse me, orthogonal non-identifiability q. Again, because if I take x and I right multiply it by an orthogonal q, the inner products all stay the same. These inner products are unchanged, and so the probability over networks is unchanged. Okay. Right? In other words, we want to, so modulo that rotational non-identifiability, I want to have some estimate x hat that is close to x up to that rotation. And I'm still going to be vague about what the heck that norm is for now. I promise within the next 5-ish minutes, I will tell you. Okay, and I mentioned briefly, but I just want to point out again, this you can think of as a distance on equivalence classes of x's. So instead of looking at all x's, you can look at equivalence classes of all the x's that give rise to the same expected value for a, right? And then you can think of this as just being a distance, this whole quantity, right, including the minimization, as being a distance on those equivalence classes. Okay, we use that in a recent result that's on the archive with my student Tao Yan, where we established some of the minimax rates for these kinds of problems. And if time allows tomorrow, I'll talk a little bit about some of those results. Okay, so 2 questions. 1, what should the norm be? Okay, you know what, I like, how about question mark? Right? I'm defining a new norm, it's called the question mark norm, right? And we will decide what question mark is in a minute. Okay, so first question, what should that be and why? And then 2, what should x hat be? Right, so x hat, again, is going to be some function of a, right? I hand you a, you use some procedure or other, and that procedure outputs a guess as to x1, x2, up to xn, right? And so this statistical notation is, well, I'm trying to estimate x, so my guess as to the true value of x, I'll put a hat on it, right? So this always, in statistics, denotes an estimator, right? There's going to be some random quantity. The randomness in it comes from our data, in this case a, right? And we want to design this thing so that with high probability, and in this case, I mean with high probability in the vaguest sense, right? Maybe very, very high in the sense of like, you know, exponentially small in the size of the data, or just, you know, bigger than a constant. I don't know. We'll specify that soon. But you know, I want it to be very likely, somehow or other, that x hat is close to the true x. Okay. All right. So to answer question 1, I need to take a slight detour. Why do I want to estimate x in the first place? Right? We said that in the special case where we recover something like the stochastic block model or the degree-corrected stochastic block model or any of these kinds of models, we said that the x's here really just capture community and, you know, popularity information, you know, whatever kind of, basically the model parameters associated to each vertex are encoded in x. So if there is a block structure present in the model, right, meaning there is some kind of community structure, that structure will be reflected in these x's, right? And x's, latent positions, xi's, corresponding to the same, corresponding to vertices in the same community, are going to, again, depending on the model, either be on a line, like on an array, that happens in the degree-corrected stochastic block model, or they'll be sort of in kind of like the same chunk of the simplex in the mixed membership stochastic block model. So somehow or other, and in the plain old stochastic block model, these will just be, right, there will be k point masses, 1 point mass for every one of our communities, right? And every one of these xi's will be at one of those points. Okay? So in all of these different cases, we can describe basically how these x's ought to behave. And then we can cluster the rows of x hat accordingly, right? So let's just think about the simplest case when we're in an actual stochastic block model, right? No popularity parameters, no nothing. Right? In that case, the x's, every xi is one of k point masses. Think of it this way, right? B equals, let's call it x tilde transpose, right? Where x tilde is k by k, right? And the rows of this thing, say x tilde little k inner product with x tilde little l, is exactly b sub kl. Okay? And then remember that under the vanilla stochastic block model, the expected value of a, let's use b and z here, equals z transpose okay, just as a refresher, remember we thought of encoding the community memberships of the vertices in these one-hot encodings, the rows of Z. Okay? So when my data actually comes from a stochastic block model, the expected value of A will have this nice block structure once we reorder the vertices so that, say, the first community is first, second community is second, and so on. Okay? That's going to be precisely reflected in the rows of this matrix. Right? So this would be our X, and this has exactly k distinct rows. Is that reasonably clear? So that's in the special case of the SBM. In the more general cases, things are a little wonkier. You have to do a little bit more symbol manipulation, but the intuition is easiest to see here. Okay. So if I know that the rows of this thing, zx tilde, x in the random dot product graph, have a nice structure, namely every row is one of k distinct types, well, if x hat is close to this thing, then the rows of x hat should kind of cluster around k distinct points as well. Right? So somehow or other, ideally, we would like to find a norm such that convergence under that norm ensures that all of my estimates of these guys, so my x hat 1, x hat 2, blah, 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 are uniformly close to the corresponding rows of x, to x1, x2, blah, blah, blah. Okay? So it's tempting at first to say, oh, let's make this the Frobenius norm, right? Or the spectral norm or something like that. The problem with doing that would be that just because this thing converges in, say, Frobenius norm, it doesn't imply that my estimates, x hat I minus xi, get close to one another uniformly fast, right? It could be that I have one really pesky vertex whose latent position just doesn't quite converge as fast as I need, right? So we're going to look at a different norm here. We're going to look at the 2 to infinity norm. Very awkward chunk of board I carved out here. Let's do this up here. We're going to look at the 2 to infinity norm. The 2 to infinity norm of a matrix M is going to be the supremum over all unit norm U's, the infinity norm, the max norm of M times U. Okay, so those of you who haven't seen these kinds of matrix norms before, in general, you have these PQ norms where you say, look in your domain space, look at all of the vectors with unit P norm, let's say, 1, right? And then I'm going to my target space, my range, and I'm going to say, and choose this thing in my domain to make the norm in the range as big as possible, right? And the norms in these two vector spaces don't have to be the same thing, right? So here, for example, we're saying, let's look at all of the operators M, right? And notice I'm not specifying M's dimension here. M is just like arbitrary M by N or something like that, right? M is going to take vectors, look at all the vectors with 2 norm equal to 1, find the one that makes the biggest infinity norm. Okay? All right, so that's like the operator, the operator view of this thing. If you're like me and really all you do is symbol manipulation, right? Like I'm a computer scientist by training, everything's just pushing symbols around. Well, this is really just the maximum row norm of M. I'm sorry, I should specify here, maximum row Euclidean norm, of course. Okay? So again, why do we want to use this norm? If you converge to 0 in the 2 to infinity norm, it means that you're converging uniformly over the rows. So in particular, right, if x hat minus xq, I'm sorry, there should be a min here. 2 to infinity norm. If this thing, is say little o of 1, right? And only if if and only if, again, accounting for my non-identifiability here, oh my goodness. Okay, so writing that we have convergence in the 2 to infinity norm means precisely that, oh my goodness, I'm sorry, I've corrected this thing and then dropped an entire min over q, max over I, excuse me. Okay. So if I'm converging in infinity, in 2 to infinity norm, precisely that means I'm recovering all of the x's uniformly. I recover all n latent positions in the network uniformly over the vertices. Okay. Okay, so we've addressed this point. Okay. Now what should x hat be? Well, let's first remember that expected value of A under some choice of x is x transpose, right? But that also equals x q transpose q. So we're free, in a sense, to pick any x we like to be a kind of canonical representation, right? And not, okay, that's an awkward way to phrase that. We can't literally just like go and construct an x. I mean, you hand me x, I can choose any q here that I like, right? And I can just rotate x on the, or multiply x on the right by that q, right? And I haven't changed anything, right? The problem is no easier or harder. So in particular, let's use the special decomposition on the expectation of A to write that this is U, S, U transpose. So here, U is n by k, has orthonormal columns. Okay, and S is k by k and diagonal. And S is the k non-zero eigenvalues of that matrix in non-decreasing order. Okay. Because we're in the random dot product graph, all the eigenvalues here are strictly positive. I can take the square root of s. I'm going to rewrite this in this way. Oops. Okay, so all I did was take the square root of s, factorize it out, and tuck it in with the U transpose on the right. Okay. So our canonical choice of x put it in quotes, can just be this. Right? Again, I'm free to rotate x any way I like. Right? I know that if I choose x to be, if I pick this thing, I can always rotate it somehow to match the inner products of this. So without any loss of generality, we're just going to assume this is the true x. Okay? I want to mention as an aside that yesterday, Joao pointed out to me that this x has orthogonal columns. I have no idea if that's useful for us or not. But just like, I don't think anyone in the literature has bothered to make use of that fact. and I'm not sure it really helps us unless we care a lot about something called interpretability. If you think a lot about regression and you want to be able to somehow like identify the columns of this thing, right? Well, maybe the fact that these columns are orthogonal helps you, right? Like we like it when the columns of our design matrix are orthogonal. Like that's a nice property. Just an aside, and if anyone wants to like dig into that idea more, let's chat. Okay, end of aside. So this is going to be our canonical choice of x. Okay, and now I'm going to do the most statistical thing ever, which is, so in statistics, there's this thing called the plug-in principle. And it's when you want to estimate some quantity, and that quantity is expressed in terms of other parameters in your model, how should you estimate that quantity? Well, you should just estimate each one of the individual parameters, and then your overall estimate is like you glom all those parameters together. So here's a u, and here's an s. And I'm going to imagine that we have an estimate u hat. Sorry, so I'm going to write x hat by just saying, let's hope we can estimate u hat, and hope we can estimate s. So imagine that we have a u hat and an s hat, and I'll just plug them in here. Okay, so this is the plug-in principle in statistics. Right, I have some quantity that I want to estimate. I'm going to get estimators for each of the terms that make it up, and I'm going to just put hats on them. And provided I can estimate these two things, then under basically as long as you can apply something like the portmanteau theorem, then kind of everything's going to go through for you. You'll get whatever consistency properties you want, as long as the transformation from u hat or from us to this quantity is not too messy. Right? Okay. So like we statisticians are simple people. Like you show me a quantity to estimate, and I will just, well, I'm going to estimate the pieces one at a time and hope that I can like triangle inequality my way to victory. Right? In this case, you can't just triangle inequality your way to victory. Proving that this thing is close to this thing, it actually takes quite a lot of work. I'm going to sketch a little bit of that today. We're not going to go into the gory details because it's just a bunch of linear algebra and like adding and subtracting things. But I want to just point out very briefly, if you try to naively just say, let's triangle inequality, u hat minus u times s 1/2, and then you'll have like a u times s hat 1/2 minus s 1/2, that doesn't quite work. It's not going to get the best rate that we know anyway. You have to be a little more clever. Okay, so let me give just, I'm going to quote just a representative result from this literature about how x hat is close to x, and then we'll talk about how we actually prove a result like that. Okay, so this is just representative. This is hardly the optimal bound at this point. This paper is like a decade old now. But so this is my co-advisor, Vince Lazinski. Dan Sussman, Avanti Athreya, and my other co-advisor, Carrie Preeb, 2014. Okay, I'm going to just, again, this is sort of stated informally because, like I said, we're going to drop, like we're not even paying attention to sparsity, for example, but just, so morally speaking, x hat minus xq, this thing goes like a constant that doesn't depend on anything else up here. Times the dimension, times log to a constant power. I think c is like 2 in this result, divided by root n. Okay. So I want to stress this is like informal. So in the original paper, for example, they show how like this bound actually ends up depending on, for example, the maximum expected degree in the numerator. Depends on some spectral properties of basically properties of S here in the denominator. right? But if you kind of translate it to the setting that we're in here today, right, all those things basically cancel out. You're left with a root n down here. Okay? And if you care about the sparsity, what you pick up is that there's an n. So inside that square root there, you get a rho n, provided rho is like little omega of, actually provided that n times rho is little omega of like log, it's a c prime. And I apologize off the top of my head, I don't remember exactly what this constant is. It's something like, you know, log to the 4. Right? So c and c prime here, these little constants are small. They're not like 20. They're like a half, 2, 4, something like that. Okay? I'll give my sparsity rant a second time just because I think it's an important point to drive home. I interact with lots of probabilists who they see log factors floating around in statistics results and think like, we got to get rid of that. And the math nerd in me agrees, because like the cool math happens when you try to get rid of these log terms. Like I said, like I myself have written like a couple of papers now about how to shave some of these factors off. So like it's super fun to think about. But I also see this like kind of contrary attitude among a lot of probabilists who think if there's a log factor floating around, like you should be ashamed and like you can't share this with the statisticians yet. Don't like break free of that thinking. Statisticians don't care about the log factors for the most part, except in, you know, theory papers, I would say. Right? Like, okay, fine. For minimax results, right, when you want to prove what's the best possible estimation rate, yeah, you want to get rid of log factors, of course. But if you have an estimator and like it's good up to some log factor, don't let that stop you from like just running, right? Log n is a constant in practice, right? Like log of all the particles in the universe is like 300. Okay, good. I gave that exact same rant yesterday. I just wanted to do it again because I think it's an important thing to bear in mind. Okay, so again, I'm ignoring sparsity in most of what I'm saying today. It's just highlighting here in bright orange. If you care about the sparsity, roughly speaking, this is what you end up with.
Sorry, this is a result of holding high probability or something?
Oh, thank you. So it's actually stronger than that. So this is one. Thank you for asking that question, because it jogs my memory to mention something that I want to bring to people's attention. All these kinds of results actually hold with probability at least 1 minus something that's like polynomially small in n. Well, this is my third little constant floating around. So, I mean, I can make this constant as big as I like at the expense of basically inflating c here. Okay? And so this is where, remember, our results about detection in the stochastic block model only said that, you know, in the large n limit, the probability that I recover everything is 1, right? This says something stronger, right? Once c is bigger than 1, right, this says that eventually, almost surely, I get this kind of recovery, right? And as long as the B matrix isn't too hard, like the gap basically between the gap between P and Q and the sparsity aren't kind of too hard, I'm going to be able to get agreement 1, right, perfect recovery, asymptotically eventually almost surely. Stronger result, right? With probability 1, there exists an n such that for all n bigger than that, I'm going to get perfect recovery, right? So for this reason, like again, there are people say in the literature that like spectral methods are weaker than, you know, these other kinds of like, you know, AMP-based methods. That's true if you evaluate them on the criterion of weak recovery. On the other hand, you can't usually, to my knowledge, get these kinds of guarantees for AMP. But maybe Cynthia should set me correct on that. I don't actually. I'm saying that like I think that's correct. I don't know for sure, right? I'm not an AMP expert. So they're like kind of incomparable in some ways, and this kind of gets at that. So thank you for that question. Right? Let's, like, in the interest of fairness, what's the trade-off, right? For those for those detection results, rho can be like 1 over n, right? And for these results to work, we usually need rho to be a little bit bigger, but just by log factors. And log n is 300. Okay. I'm going to make that joke again and again until people actually laugh at it. Thank you. Okay, great. So in the rest of today's lecture, I want to hopefully explain how we go about proving results like this one. Okay? I'm not going to show you the most optimal result because we have 40 minutes, right? But I am going to show you enough that you could like go and read the paper without a lot of trouble, right? Or read papers in this literature without a lot of trouble. And more importantly, like for the grad students, not all of whom work in exactly this area, I want to highlight a couple of useful tools that are presumably useful not just for proving exactly this kind of a bound. Okay, so this is a good time to pause for questions and for me to wish that I had more coffee and instead drink some water. For clarity, that was not a like passive aggressive someone get me coffee. I'm okay. Okay. All right, so how do we get a result like this one? Like I already mentioned, this typically involves a lot of clever adding and subtracting of quantities. Like the caveman mathematician in you wants to just like triangle inequality these two things a couple of times and be done with it. And if you try to do that, it's not quite enough. You're going to end up with a couple of factors that grow like constants or even root n, depending on exactly what you do. Okay. And we want to end up at a result that looks more like 1 over root n up to some log factors. So I'm not going to show you the full details of that like add and subtract scheme. Instead, I'm going to just quote to you a result from a paper that I wrote during my postdoc with Asad Lodia and my postdoc supervisor, Lisa Levin. So this is L, another L, and another L. 2022. This is in JMLR, Journal of Machine Learning Research. Okay. So let's write P equals X transpose here, just for ease of notation. And this error that we want to control in 2 to infinity norm can be expressed in terms of 3 factors. The first one looks like another 2 to infinity norm. And I'm sorry, this equals U, S, U transpose. Right, so I'm just using the exact same notation we had over here. Sorry for a slight almost overload of notation. This is kappa, the condition number. This is k, the dimension. I'll try to be careful to make them look wildly different. I apologize. Okay. So you do a bunch of clever adding and subtracting of terms. And then you apply the triangle inequality, and you use some properties of the 2 to infinity bound. Okay. So like kind of 2 key ideas here. Why this works. One, a clever decomposition. And that clever decomposition I cannot claim the credit for. This is due to Min Tong over a period of papers that he wrote with other folks at Johns Hopkins. So I'm not even going to try to recite that whole series of papers, but if you look at Min Tong is now at North Carolina State University. You can look at a bunch of his papers from about 2012 to 2020, 2022-ish. Develops this kind of clever series of adding and subtracting things here. And then properties of the 2 to infinity norm. The most important of them being that the 2 to infinity norm of M is less or equal to, the 2 to infinity norm of a product is at most 2 to infinity of the first thing times the spectral norm of the second one. And for more about the pseudo-infinity norm, there's a great paper by Joshua, who's here with us for, I think, the whole month. Also Min and Carrie Priebe at Johns Hopkins. This is from 2022. No, that's wrong. 20-something, 2018 maybe? I didn't write it down. I believe that's 2018. Okay. I'm sorry? I didn't understand your question. Both are true to infinity?
Yeah, both.
That's not the case. The second one's a spectral norm. Yeah. So the 2 to infinity norm of a product is the 2 to infinity norm of the first one times the spectral norm of the second one. Sorry? Of the second one. Maybe I can write this bigger so you can see it, and then I'll erase it when we go to this board. I wrote that, and I'm sorry, yeah, I wrote pretty small there, I see now. The 2 to infinity norm of a product is at most the 2 to infinity norm of the first one times the 2 norm of the second one. If you want, like, super clear, like, put a 2 there. Yeah. Thank you for the clarification. I'm sorry, I didn't, you stand up so close to the board, and then, like, as an audience member, I'm always watching the screen, and then, like, oh, that writing is huge, right? It's not. I'm sorry. So this jumbled mess in the corner here is this. So I'll leave that up for a second, and then I'll erase this before we go on to the next board. Okay. Thanks for the clarification. Okay. I'm sorry. My boardsmanship here is leaves something to be desired. So if I want to control this thing, I just have to control these 3 terms. Lambda k of p is not under our control. It's going to grow linearly when we're not in the sparse regime. It's going to grow like n times the sparsity when we're in kind of the normal sparse regime. You can play additional games by allowing the condition number of p to not necessarily be 1. Right? So if, for example, the largest eigenvalue of p is growing at a faster rate than the smallest eigenvalue of p, this problem gets a little harder. I'm going to, for the sake of our sanity today, just assume basically that this thing is always 1. I just want to point out that that further complicates the story if you actually keep track of that factor there. So we point out 2 things. So in another paper by Joshua, Min, Carrie, and then in addition to the 3 of them, Patrick, Ruben, Delancey, the 4 of them proved a slightly nicer version of this trick in a more recent paper where they were working with the generalized random dot product graph. So basically, it gets more or less the same rate up to shaving off some of these dependencies on like the game you have to play trading off, say, kappa against lambda here is a little less annoying. Okay? But all these tricks basically get you the same rate, morally speaking. Okay. I should also point out that at this point, all of these kinds of, for proving specifically these kinds of results, these kinds of add and subtract tricks they still work, they're fine, but they've mostly been superseded by leave one out analysis. And I think Joshua will tell you a bit about those techniques next week. I don't know for sure. So I'll just mention, like, there's I don't know if better tool is the right, leave one out. So this is a family of methods that's kind of superseded this. It kind of relies on this intuition that when I perturb a matrix, right, I really shouldn't perturb the leading eigenvalue or the leading eigenvectors very much, right? And you do a little bit of kind of clever analysis tricks. The best reference for this would be a survey by Chen, Fan, and Ma, 2021. And the title is something like Spectral Methods for Data Science or something like that. Okay? So these methods don't achieve better rates than this kind of add and subtract, but I mentioned these methods because they're a little more general. Okay, so I'm showing you slightly out-of-date technology, I guess, is the short version. I think the important point here is that we're now going to see some tools for controlling a couple of these terms that are useful no matter what area of probability you're working in. Okay, so I'm going to erase my magnified view here. Okay. So I want to control some of these terms, and we're not going to look at all of them here today. We're going to talk about just two. We're going to talk about this guy. I'll highlight them. We're going to talk about how to control this and how to control this spectral norm. Well, you can barely see that. Let's try a different color. We're going to control those two guys. And the main tool we're going to use is concentration inequalities. So these are basically, first and second moment methods, but a little bit more careful. As Dieter promised this morning, we're going to start with kind of the concentration inequality that gives rise to all the others, and that's the celebrated Chernoff bound. So the Chernoff bound says that the probability of a random variable z being bigger than t is at most e to the negative lambda t times the MGF evaluated at lambda, and this is for any non-negative lambda. Okay, so the probability that some random variable z is bigger than some value t can be bounded in terms of its MGF and a kind of penalty factor evaluated at some particular lambda. And you can get the same result here. Let's see. Right, so for the left-hand tail, we need to be a little bit more careful. We have the same bound, except that lambda needs to switch signs. Okay, one-line proof of this fact. So the probability, I'm just going to do this one. The other direction is straightforward. Probability that z is greater than or equal to t is exactly equal to the probability that monotone function of z is greater than or equal to the monotone function of t. So I'm going to choose a monotone function, namely being raise the thing to, raise lambda times the thing to the, exponentiate lambda times the thing is our monotone operation. So this is, okay, so all I did was apply a monotone transform to both sides of this guy. Okay, and then by Markov's inequality, this thing is at most expectation e to lambda z divided by e to lambda t. Okay? And so in this equality, we used this equality where we used the fact that lambda was non-negative. Okay? For the other direction, of course, lambda needs to be non-positive. Okay? Now, I have the pleasure of quoting Luke from, was it yesterday or 2 days ago now, when he said that you should always just start from the Chernoff bound and optimize over lambda, right? You're always going to do better than if you just kind of blindly apply a concentration inequality. It is my great pleasure to show you exactly what happens when you do the silly thing and don't try and optimize this first. So it's going to be left as an exercise to the reader, listener, to see what happens when you optimize this. Right? And you can see examples of that in the literature. In the interest of time, I'm going to show you kind of the dumb version, right? Because it illustrates all the important points. And it's also going to illustrate for you exactly why it is that when you don't optimize here, you often lose the best rate you could get. Okay? So you know what they say, if you can't be a stellar example unto others, at least you can be a dire warning. So this will be your dire warning, right? We're going to do kind of the dumb thing and not pick lambda optimally. Okay. Is this piece I want? Okay. So as I mentioned at the start of this lecture, it's a little bit of an intimidating lecture to give because sitting in the audience are multiple world experts on specifically this topic. So I should mention right at the top here that kind of the go-to book for these kinds of methods would be Boucheron. Dossi. I think the book is literally just called Concentration Inequalities. Okay, it's a fantastic book. I'll also mention, we were talking about this book over lunch today, and how much we all love it, Verschinen's book, 2020. So both of these give great treatments of kind of the Chernoff bound and corollaries thereof. Corollaries thereof doesn't do justice to how much work goes into proving all of the downstream results, like, let's be clear. So let's make a definition here. A random variable y is nu sub-Gaussian if the cumulant generating function of y decays in a nice way, and I'll show you what that means. If cumulant generating function of y obeys, whoops. Okay, so I look at any real lambda, I evaluate the cumulant generating function of y at that lambda, and it needs to be bounded by the square of lambda times nu over 2. And we call this behavior sub-Gaussian because this quantity right here is exactly the cumulant generating function of a Gaussian with mean 0 and variance nu. Okay? And to make just a fact, this is the thing you can check, best checked in the comfort of your own home, but it's just 2 lines. Okay? If y1, y2, up to yn are independent nu I sub-Gaussian. So by that I mean that yi is nu I sub-Gaussian. Okay, hopefully that's clear from the way I wrote this. Okay, so for each y here, yi is nu I sub-Gaussian. Those nu i's don't need to be the same, but they do need to be independent. If that's true, then the sum over all I, scale my yi's by some alphas, is nu bar sub-Gaussian. And nu bar is the sums of these individual nu i's scaled by the squares of those alphas. And this should make some intuitive sense, right? Very roughly speaking, nu here should be like a variance, right? So the variance-like term, nu for this new random variable here, should have a variance like, well, the sum of the variances of all the individual things. So if I'm scaling yi by alpha I, there should be an alpha I squared here. Okay? So, great. I'm going to leave all this up because it's nice. I'm going to keep this because we need to care about it. I'm going to erase a couple of these boards here. We have about 20 minutes, which should be about what we need. Oh, I never got to resolve this. Like, we said what x hat should be. So check mark, and then I'm going to erase it, but I just wanted the victory of putting the check mark there. Yeah, I'll take this. Okay. One more fact. So here's a theorem. This is some combination of, either you view it as just a corollary of Chernoff, or you view it as some variant of Hefting, or Bernstein's inequality, or any of these things. So the bound I'm going to quote is not one of these bounds precisely, but they're all kind of in the same family, so I'm just going to mention all these names so that you have them. Bennett also is one of these. Okay, so there's a variety of bounds to kind of apply to these sorts of problems. They all have kind of their own nice properties and drawbacks. I'm not going to go into the details here, but the easiest of these bounds is that if y is nu sub Gaussian, then the probability that y is bigger than t in absolute value is bounded by, again, a thing that looks kind of like the tail of a Gaussian, namely okay, so this specific result is basically just a corollary of Chernoff. You pick lambda in a clever way, right? In a clever but it'll turn out wrong way for our purposes. I just want to mention that so you can relax this sub-Gaussian property to something called sub-gamma, meaning that the tails of your random variable are a little heavier than the Gaussian. They behave more like the tails of a gamma distribution or an exponential. You have to then change this nu to be 2 parameters, and then they both show up in this denominator. Right? So there's other results along these lines, and again, if you want to have things to Google, like Hefting's inequality, Bernstein and Bennett's inequality, but they all basically fall out of Chernoff's inequality by making clever choices of lambda and playing around with the cumulative generating function. Okay. And again, the place to learn about all of that is in the concentration inequalities book, Gabor's book, and the Verschinden text. So again, I want to reiterate, the rest of what we're going to do here, using this bound, is a bit of a cautionary tale. We're going to end up with a concentration result for, I think in the interest of time, I'm only going to look at this guy. If we have time, I'll come back and talk about this. But the tricks for controlling this, it'll be obvious how to control this afterwards. When we go to control this, we're going to see that the concentration rate we get for it is not quite what we would expect. It's going to be a little slower. Basically, we're going to not be able to account for sparsity. Okay? And that's annoying. And the cautionary tale is that's the result of not being clever in playing around with Chernoff's inequality here. If we were more careful with this bound from the get-go, we would be able to get our sparsity to show up. Okay. Okay, so how are we going to control that spectral norm? Again, I'm going to, if time allows, which I think is unlikely, we'll also talk about controlling this. But I'd rather see the important and interesting punchline controlling the spectral norm bound. Okay. So how do we control that spectral norm bound? Okay. Well, the operator norm, spectral norm, for any matrix M is the supremum over all unit norm U, M times U in norm. Okay, so we look at all of the So this is usually written either like 2 norm, or you'll even see 2 to 2 norm. Right? It kind of echoes what we were saying about the 2 infinity norm. I look at all of the unit Euclidean norm u's. I hit them all with m, and I find the value, the biggest norm of all of them is going to be my spectral norm. Okay? And again, in the literature, you'll see this either as like the unadorned norm, or like a 2 norm, or a 2 comma 2. They all typically mean the same thing. You do need to be careful whether this is meant as like a vector norm. Like it's always good to pay attention to these things. Okay. Now, if you were fixed, let's talk about what would happen. So maybe fact, or I don't know. It's a fact that we're going to prove, right? For fixed u on the unit sphere, how does A minus P times u behave? Well, so this will become a proof, and then the punchline will be that we get a bound here. Okay. Let's square this because it's easier. All right. This is the sum over all I. And then I look at the row inner product between the ith row of A minus P and U, and I need to square that. Okay. So let's look at one of these. So let's fix I in N. So I'm fixing one row of A minus P. Okay. In other words, the size of this inner product. So I look at the ith row of A minus P, I inner product it with my fixed U. Okay. I'm sorry, let's not take the absolute value yet. This thing, right, is a sum of uj sub Gaussian random variables. I'm sorry, I should say that it's independent. Okay? Right? And I apologize the fact that I did not mention for you yet that if y is Bernoulli, probability p, then y is 1 sub Gaussian. You might already see why things are going to go wrong for us in terms of getting a sparsity result here, right? In the sparse case, all the entries of A minus P, like most entries of A are 0, right? The variance of most of these entries is really small. And that variance, like this term here, doesn't depend on P at all. And yet, morally speaking, it should look like a variance, right? It should be like P. So we're not going to be able to say anything about the case where all of the entries of P are very close to 0. Okay, so you're already seeing where this is going to be the suboptimal bound, right? If you want to see how to make it a much more optimal bound, you can go to Joshua's lectures next week, where we'll talk about kind of one set of techniques for more carefully combinatorially studying the behaviors of this thing. You can also read one of my favorite papers, and I don't say this to embarrass Roberto too much, but Roberto's paper from 2009, which was the first in a lengthy series of papers to show how to show concentration inequalities for this as a matrix, right? So instead of trying to shoehorn all of this into scalar land, you say, all right, I have a random matrix. What can I say about its norm working with it as a matrix? Okay, so 2 different sets of results. There are also follow-up papers with those matrix techniques by Joel Trope. I'm not going to talk about either of those families of results. For the careful combinatorial analysis, talk to Joshua this week or attend his lectures. And for the matrix version, well, a world expert is sitting in front of you. Not to put you on the spot, Roberto. Okay, so I'm showing you, but I'm going to show you the set of tools we typically use for some of the kind of the easier version of these bounds, and like the reason I'm showing you this easier bound is because we're going to see a useful tool for proving these inequalities in much more general situations, like well beyond matrices. Okay. So here I have a sum of n independent uj sub-Gaussian random variables, right? If I have a one sub-Gaussian random variable, namely one of my centered Bernoullis here, and I'm sorry, this should be y minus p, right? Anytime we're talking about sub-Gaussian, sub-gamma, any of these kind of concentration properties, our variables need to be centered. So my apologies. Okay? Correction here is that this is a centered Bernoulli. Okay? What did we say? We said if we had a bunch of independent nu I sub-Gaussians that are all scaled, then the sum of the scaled random variables is itself sub-Gaussian with a parameter nu bar that's like the weighted sum of the individual sub-Gaussian parameters. So every one of these a minus pij terms is one sub-Gaussian. Right? So therefore, sum over all j, ij, entry, that guy, is okay, so each one of these is one sub-Gaussian. I'm scaling them all by u sub j. So in the end, I'm sum over all j, uj squared sub-Gaussian. U is a unit vector. This thing just equals 1. Okay. So if we now go back and use, where did I state our, oh, right, so now we're going to use this bound. Okay, so the probability that rho j, a minus p I j uj is bigger than or equal to t. This is just t squared over 2. Okay. Okay, we're almost done. We controlled one of these, right? But I have to control n of them, so I need to make a union bound over all the I in n. Oh my gosh, a union bound over all the rows of a minus p. And I'm going to take t, what do I want to take t equal to? It's like constant times square root log n. Okay, and this thing becomes, this thing is less than or equal to, what do I want to say? Should just be root n? Yes. Up to some constant. Oh, no, excuse me. Good. Boy, okay. Right, so there are n such rows. Now, this would be fine, except for a problem here. In the spectral norm, I'm taking a supremum over all u. So if I had a fixed u and I wanted to know what a minus p does to u, we'd be done, right? Okay, but now the game is different. I don't get to fix a u and then have the randomness happen. It's like u gets to look at the randomness in a minus p. Okay? So what we want to do somehow or other is a union bound over the unit sphere, right? Okay, the unit sphere unfortunately has a few too many elements at the party to make that feasible, right? So the key idea here is going to be something called an epsilon net. And we're going to talk about this, and then we're going to call it a day. notes that I want to talk from now. Great. So I'm going to erase this fact here. I apologize for that. So we want a union bound over the unit sphere. Okay, but like, you can't always get what you want. It's the philosopher Mick Jagger. Okay. So instead, we're going to look at a subset of Sn. And the intuition, if U and V are close, then A minus P of U and A minus P applied to V are close. Okay. Now, I showed you this for two reasons. One, controlling this, we basically immediately see how to control this guy, right? If I can control A minus P times a U, well, this capital U here has just k different columns. Each one is a unit vector. So I'm going to apply that argument k times, one for each of the columns of U. I'm going to incur a factor of k in here because of the union bound over k. Right? But I can basically control this thing. If I want to control this, at first you think, great, let's cover the unit sphere in enough specific points so that kind of every point is epsilon close to some representative. Okay, I'll formalize that in just a second. Right? You might think just like consider enough different choices of U and look at this quantity and you're done. But if you do that naively here, you end up with an extra factor of root n hanging around. So we need to be a little more careful. There's another property of the spectral norm, namely that the spectral norm of M is also, and this is like Rayleigh-Ritz kind of results in your algebra, the supremum over, again, looking at all elements of the unit sphere and look at the quadratic form in them. Okay? Now we're running out of time, so I'm not going to show you the detailed proof, but it runs by basically exactly the same argument here, right? Except instead of UJs here, you have UI UJs, right? If I left multiply this, if I hit this on the left with a U transpose, this expansion looks very similar, but now I get UIs and UJs here. The basic idea is going to be we're going to control for a bunch of U's. So the same intuition here, the idea that if U and V are close, then the quadratic forms should be close too, right? That's going to kind of do the trick for us. So we need one definition. N sub epsilon is, and this is a subset of Sn minus 1, is an epsilon net for Sn minus 1 if I look at any element of Sn minus 1, then there exists some U naught in this set such that U minus U naught is epsilon small. Okay, so it's like it's literally like you cast a net over the unit ball and like no, or the unit sphere rather, and like no individual point on that sphere can get away. Right? Everything is within epsilon of some point. The point is that we can find these things, right? This is just a fact. Again, this is the easiest place to find this is in Verschinen's book, but this is also discussed a lot in the empirical process literature. For Sn minus 1, the size of n epsilon grows like 3 over epsilon to the n. This is not the best possible bound. It's more like 2 minus epsilon over epsilon, if I remember correctly. But for our purposes, this is fine. Okay. We're almost done. So I'm going to erase this board because like the only thing you have to remember at this point is that we want to control this thing. Okay? We have 1 minute. I'm going to give you the, it'll take probably 2 minutes, but I promise not to go over much. This is a fact. It's not hard to prove. It's a nice, it's actually an exercise in version in the book, I believe. Let n sub epsilon be an epsilon net for Sn minus 1, then m is at most 1 over 1 minus 2 epsilon times the sup over all u and epsilon of a quadratic form. Okay. The proof of this is basically just like two lines and a triangle inequality. It's a fun exercise. You basically use linearity of, like, treat this thing as an inner product. Use linearity of the inner product, and then you want to use the fact that there always exists some u star in Sn such that m times u star has norm exactly this spectral norm. So you have to use the fact that there exists something that achieves this supremum, and then you're going to look at the closest thing in the epsilon net and compare the quadratic forms. Then you just triangle inequality your way to victory. And if anyone wants to see details, they're going to be in the lecture notes, and happy to talk offline. OK, we're nearly there. Basically, so I'm going to give a proof sketch of the fact that theorem a minus p is at most like root n with probability at least 1 minus order like n, again, to the negative little c, where you can make this little c bigger by making this big C bigger. Okay? Very fast sketch, right? Essentially, we need to control this quantity. So fix some u in my epsilon net, right? U transpose a minus p times u is going to be less than or equal to like c square root log n. Okay, with probability at least 1 minus n to the negative, I don't know, call it. Okay, this little c and this little c are going to be off by 1 or 2 from each other. It's not going to bother us. Okay. Then we're going to take a union bound over the epsilon net. We're going to incur a factor of n here, right? And oh, excuse me, I got ahead of myself here. This is, I even wrote in my own notes, it's tempting to take this to be root log n, but that's not quite what we can do. This is less or equal to root t, whoops, not root t, with probability 1 minus order e to the negative t squared over 2. I apologize. So now we're going to take a union bound over all n sub e. And so the probability that the max over the u in my epsilon net of that this guy is bigger than or equal to t, going to be less than or equal to, well, I need to take a union bound, so I'm going to have size of n sub epsilon times exponential of negative t squared. And I have to inflate this a little bit for some reasons that will be obvious when we chase down constants, which we'll do in the comfort of our own homes. Okay? So I apologize for going a little fast here because we're already 3 minutes late for coffee. Now, the last step here. We just said, somewhere I wrote it, the size of this epsilon net is like exponential in n. So I'm going to have to pay an n factor in here, and I need to choose t big enough to cancel it out. Well, I'm going to choose t to be root n, so that t squared is n, and I need to add on a little bit of extra stuff to get a log n factor up here so that I can make sure that I get back my c here. Okay? So the last step is just choose, we almost ran out of board, take t equals c root n times like some, what, log n or something like that for c suitably big. Okay, and we're done. Okay. Thank you all for your time and attention. My sincere apologies for going over. It's something I really genuinely don't like doing. I also hate hearing myself talk, so like, it's the worst. Okay, thank you all for your time and attention. Let's do questions offline. No need to keep everyone standing around. Thanks so much. See you tomorrow. Seriously, go get coffee. Tomorrow's lecture will start 15 minutes late. 15 minutes late. Oh my gosh. I will not be here 15 minutes early.